In the last video, we discussed about inverse trigonometric functions and mainly we spoke about sin x and sin inverse x. The same logic can also be applied to all other functions like cos x, tan x and the remaining other functions sec, cosec and cot. Let me once again look at sin x. This is a graph of x versus sin x, which means x is on the x-axis and sin x is on the y-axis. To find out value of sin x for any given value of x, we locate the value of x on the x-axis, we draw a vertical line from that till we hit the sin x graph and draw a horizontal line from there to find the value of sin x for a given value of x. A similar procedure can be employed to find out the value of sin inverse x for any given value of sin x. If value of y is known, if this is the value of y and we need to find out the value of sin inverse y for this y, we would draw a horizontal line from here till we hit the graph and then draw a vertical line from there to find out the value of sin inverse y. If this is y, then this becomes sin inverse y. The problem here is this horizontal line would cross the graph at multiple points, so hence we will get multiple values of sin inverse y for a given value of y, like this one, then again here, then if I extend further, again this would be the value of sin inverse y for the same y, and on this side as well. So there are infinitely many values of sin inverse y for a given y, and to restrict the value of sin inverse y to one value, we take one section. If you look at this graph, we can make sections of the graph like this. Any one section from here to here, another section being from here to here, another being from here to here, or from here to here, or from here to here. Any one of these sections can be used to find out the value of sin inverse y for any given value of y, and any one section will serve equally well for the whole range of y, right from -1 to +1, or right from +1 to -1. Any one of these sections can be used, and one of these sections, I would say rather arbitrarily, has been named as principal value range. In case of sin x, that happens to be this section. So while I would say the same graph can be used to find out the value of sin inverse y for any given value of y, the only difference being in this case we start from the y-axis, draw a horizontal line, and where it hits the graph, we draw a vertical line from that place. It is, however, customary to use the given value on the x-axis and the function on the y-axis. So the value for which we want to find out sin inverse should be on x-axis and the sin inverse should be on y-axis. Here it is. If you notice, it is the same graph, only the axes have been inverted, have been exchanged, and in dotted line I have shown the rest of the graph. The dark portion is the principal value range of sin x. So here, if you give me a value of x, I can draw a vertical line and till I hit the graph, then draw a horizontal line and find out the value of sin inverse x. The range and domain of the function sin x. Value of x can be anything from -infinity to +infinity. So we say domain of sin x is x belonging to the interval -infinity to +infinity, and the corresponding value of sin x will always be between -1 and +1. So we say range of sin x function is from -1 to +1. when we come to sine inverse, the range here becomes the domain of sine inverse. I cannot find sine inverse of a value which is greater than 1 or which is less than minus 1. Logically speaking, I would expect the domain of sine x would become the range of sine inverse, but because of this principal value range business, it doesn't happen, and the range remains restricted to minus pi by 2 to plus pi by 2. That is what is shown here, the range on the vertical axis, minus pi by 2 to plus pi by 2. Now let us do a similar exercise for cos x and cos inverse x. Here is x versus cos x, a very similar looking graph. Only difference being, for x is equal to 0, sin x was 0, cos x becomes 1. For x is equal to pi by 2, sin x was 1, cos x becomes 0. So it's a graph essentially shifted leftwards by pi by 2. So using the same method, I can use any value of x, draw a vertical line till I hit the graph, then draw a horizontal line from there and find out the value of cos x. So for cos x, the domain, like before, is x can be any number, any angle, value of x can be any angle from minus infinity to plus infinity. And range, again, like sin x, can be any number from minus 1 to plus 1. If I wish to use the same graph for finding the value of cos inverse x, again like before, I will have multiple values, and if I wish to divide this graph into sections, these are the possible sections, such that using any one of these sections, any one of these or this or this or this, given a value of cos x anywhere in the range from minus 1 to plus 1, I can find a corresponding value of x. So any one of these sections is sufficient to give me one value of cos inverse. Again, I would say rather arbitrarily, but the section which is defined as the primary value range of cos inverse x is this one. So given a value of y anywhere in the range of minus 1 to plus 1, when I try to find cos inverse, I would land up in a value of cos inverse y in the range of 0 to pi. Oh, this was supposed to be range of cos x, not cos inverse x. Apologies for the error. As in the case of sin x and sin inverse x, we can draw cos inverse, which would be just the same graph replicated here with axis exchanged. So this becomes the value x and this becomes the value cos inverse x. The whole of the graph is reproduced here in dotted line. Only this section is used for principal value range. So value of x can range anywhere between minus 1 to plus 1. For value of x anywhere outside this range, cos inverse does not exist. And the value of cos inverse, the principal value range of cos inverse is from 0 to pi. Moving on to tan x and tan inverse x. Now tan x graph looks quite different from sin x and cos x, because for x is equal to 0, tan x is 0. As x increases, tan x increases, and it increases very sharply. As x reaches closer to pi by 2, the value of tan x suddenly shoots out of the roof and becomes large and large till very close to pi by 2, it becomes very close to infinity. Very strangely, the moment it crosses pi by 2, slightly higher than pi by 2, the value of tan x is still very large, close to infinity, but instead of the positive value infinity, it becomes negative infinity. And then as value of tan x from pi by 2 it increases towards pi, the value of tan x comes down the roof closer to real values, and then as x reaches pi, tan x becomes 0, and then the same behavior repeats. Any section of this graph from minus pi by 2 to plus pi by 2, from plus pi by 2 to 3 pi by 2 looks identical, starting from minus infinity and going crossing 0, then going up to plus infinity. So the domain of tan x as before, value of x anything from minus infinity till plus infinity. The range of tan x, value of tan x anything from minus infinity to plus infinity. Now if I have to take tan inverse of a given value y, I will locate the given value y anywhere on this vertical axis, draw a horizontal line till it hits the graph, draw a vertical line from there and find out the value of tan inverse for the given value. So in this example, somewhere here becomes tan inverse of 2. As before, if we have to draw a graph of tan inverse x on the vertical axis, value of x on the horizontal axis and tan inverse x on the vertical axis, here it is, with the axes interchanged, and we, as before, we take any one section out of this so that we get only one value of tan inverse x. So the section selected here is this one. This section of the graph is used for principal value range of tan inverse x, which is shown here in the dark, and the other alternate value ranges are shown in light in dotted lines. So for tan inverse x, so the value of x for tan inverse x can range from minus infinity to plus infinity. For tan x, domain was minus infinity to plus infinity. For tan x, value of x could have been anything from this minus infinity to plus infinity. So I would expect that for an inverse function this would become the range, but because of this principal value range, that means I would take only this section for talking of tan inverse x. Talking of tan x, all these sections are valid. Talking of tan inverse x, I will take only this section. So the range of tan inverse x becomes, considering this graph, it becomes minus pi by 2 to plus pi by 2. Also note that since x cannot have a value of infinity, either positive infinity or plus infinity, it can have very large values but cannot be infinity. Hence tan inverse x cannot exactly touch minus pi by 2 or plus pi by 2. This remains an open interval, which means minus pi by 2 and plus pi by 2 itself are not included in the range. So here is a summary. For sin x, domain x can be anything from minus infinity to plus infinity, and range of sin x would be minus 1 to plus 1. Correspondingly, for sin inverse x, domain becomes what was the range of sin x, minus 1 to plus 1, but the range of sin inverse x gets restricted to minus pi by 2 to plus pi by 2. It doesn't become what was the domain of sin x. Cos x, the domain of cos x, value of x can be anything from minus infinity to plus infinity, and the range of cos x is from minus 1 to plus 1. Correspondingly, cos inverse x, whatever was the range of cos x becomes the domain of cos inverse x, minus 1 to plus 1, but the domain of cos x, which was minus infinity to plus infinity, does not become the range. Rather, cos inverse x gets restricted to 0 to pi. For tan x, domain value of angle can be anything from minus infinity to plus infinity. value of tan x ranges from minus infinity to plus infinity, but when you take the tan inverse, the range of tan x, which is minus infinity to plus infinity, becomes the domain of tan inverse. The domain of tan x minus infinity to plus infinity does not become, because if I take this, I will end up in multiple values of tan inverse. So the range, instead of becoming from minus infinity to plus infinity, it gets restricted from minus pi by 2 to plus pi by 2.